We are going to continue with Alok's technical seminar. Tell us about Corolla polynomials.
Start?
Yes.
Okay, so just quickly recall two examples of associahedron. If you remember, in the case of n equal to 4, there was this two-dimensional space labeled by two coordinates, and as we saw that this ABHY associahedron was a one-dimensional polytope, which was basically this equation. This is something we saw last time, where C was any positive constant. And then in the case of n equal to 5, we could draw this ABHY associahedron, which was a two-dimensional polytope in any two-plane, which was parameterized by coordinates whose chords don't intersect, like 1, 3, 1, 4. And then in this plane, for example, we saw that this was the realization of associahedron, where these boundaries were x14 equal to 0, x13 equal to 0, x35 equal to 0, x25 equal to 0, and x24 equal to 0. And this is 45 degrees. 9. Okay, so I won't give more examples now, but we had spent some time understanding at least this geometry of associahedron, how it came. Now, the commonality between these things is that these are geometries which are, so for example, this one is a one-dimensional geometry and it has boundary of 0 dimension. This is a two-dimensional geometry and it has a boundary of 1 dimension as well as 0 dimension. And so this class of geometries which have, if it's an n-dimensional geometry, then it has boundary of all lower dimensions from n minus 1 to 0. They are called positive geometries. So these are examples of positive geometries. And there is a nice result in algebraic geometry that if you give me, again, it has a priori nothing to do with physics. If you give me any positive geometry which is sitting inside, the result is actually more general. These are all linear geometries, but you could envisage that you have some curved geometry of dimension n, which is boundary of all codimension. So for all such positive geometries, there is a nice result that given any such geometry which is sitting inside some space, ambient space, one can always find a unique form, differential form on the ambient space, which is fixed by the boundary structure of this positive geometry. So let me write the form for these two examples and I will explain what it means. So for example, in this space, which is a two-dimensional space, the statement is that once we find this geometry, I can write down a form which is the following. So how is this form fixed? It is fixed basically by saying that you should have simple pole on both the boundaries of this geometry, and every time you went from one triangle, remember, so this vertex, which is x13 equal to 0, was basically this chord, right? It signified this triangulation, and this one signified the opposite triangulation, this one. So the rule is that every time you flip one chord, the sign should change by minus. And if you define a form like this, there is a beautiful theorem that these forms are unique up to overall scaling, okay, up to some overall scaling. And so similarly, if I just write corresponding form in this ambient space, which is actually a 5-dimensional space, remember I have suppressed all the other coordinates, because remember the space here was 5-dimensional. So in this 5-dimensional space, there is a 2 form, and that 2 form I will write, and that's it. After that, we will go to gauge theory. So the 2 form is such that it should have simple pole on all the boundaries. So let me write it and it will become clear what the rules are. There will be 5 terms because there are 5 vertices. Like there are 2 terms here because there are 2 vertices. And it's a 2 form because the 2-dimensional polytope, even though the ambient space is 5-dimensional. So here it's a 1 form even though the ambient space is 2-dimensional. Plus minus x and then 2 more terms because there are 2 more vertices. So okay, I will not write it, but you see what I hope the structure is clear, right? So every time we did, remember how the signs are coming, because every time I flip one chord, so here I flipped 1 3 to 3 5, I kept 1 3 as it is, then sign changed by 1. Here sign I kept 2 1 4 fixed, I flipped 1 3 2 2 4, so sign changed by 1. If I flip this one another time, okay, so maybe I just write it, then I will get and then finally this one I could flip. Okay, so this is right now what have we found? We have found that we started with some combinatorics, we found some geometries, and they are realized in this ambient space, and we found these forms. Okay, now mathematicians are interested in this. Actually, the interest came really from this ABHY paper, that the point that these forms are related to the amplitude for this phi cube theory. So then the idea was that if you take a general positive geometry, can you classify these forms on a general positive geometry? Now it's a algebraic geometry question, because positive geometries are defined by varieties, zeros of some equations, and then we want to find, like, can you fix the form by some asking that you only have singularities on the boundaries of the polytope.
And these don't have any prior geometry?
I mean, they're determined by these positive geometries, right? They're up to scale. No, we don't, yeah. Yeah, I'm just avoiding all that. So the point is that the ambiguity is actually removed, because you really should draw this in a, yeah, you know what exactly. But it's not important for us. You think that scaling is like overall phase of the S matrix if you want, so we don't care. Yeah, okay, now what I'm going to say is that because we don't have time, there is a concrete way that these forms give us some volume on the space which give us amplitude of phi cube theory, but I'm going to avoid it simply because we are lack of time. But what I'm going to try to convince you how we go from these forms to Yang-Mills amplitudes. Tree level to begin with, tree level Yang-Mills. So people who know how to go from this form to phi cube amplitude, they should think of this as, then they will make a connection with phi cube. But even if you don't know, this is still an interesting question in its own right, that how these geometries, which have really directly nothing to do with physics, how they give us amplitudes for Yang-Mills theory, tree level amplitude for Yang-Mills theory. Okay, so that's the question. So let me now try to, now unfortunately we have to divorce from positive geometry for a minute and introduce a different class of objects, which are these Corollas. So I will just, you have to bear with me for 5 minutes. So we kind of go away from, so let me intuitively explain what I want to say, that combinatorially this Associahedron is like this, right? And now the point is that so far I haven't put really any structure on this vertices of the Associahedron, but for a entirely from an independent perspective, Cramer and his collaborators realized that, I'm paraphrasing the result for our purpose, that on each vertex of the Associahedron, one can write an abstract polynomial, which is called a Corolla polynomial, which as we will see directly gives us by some operation amplitudes for the gauge theory. Let me first explain to you what the operation I have in mind is. So if we look at this form, for example this one, it's a one form, and if we want to get an amplitude from it, which we know is a function, is a scalar function, how will we do it, right? So one way, because there is no metric equip on this, so the metric independent way, if I asked you what object will be, what operation could we do on this to get a scalar function, the obvious thing is to dot it with a vector field, right? Because this is a one form, so if there was some vector field which was of the form, so let me explain what I mean. Do by do x13, let's call this v, and let's call this omega. Then you see that contraction of v with omega doesn't involve any metric, and it gives us some scalar function, right, of x13. But this can be generalized to arbitrary forms also. For example, if I erase the 2 form, but if I give you a vector field, if I want to take a 2 form and say how can I get a scalar, then I have to contract it with what is called multi-vector field, which is of the form. So if an object like this, which somehow was given to us, then contraction of this, please ask if this is not clear, will give us a scalar function. Now, the remarkable fact from a different perspective was that Cramer et al. Showed that there was a natural abstract vector field one could write down on every vertex of the Associahedron. So, once you combine those nicely, you are getting a vector field, and that vector field, as we will argue, we will see it's such that these operations, these objects then turn out to be Yang-Mills amplitude. Like this will be a tree-level Yang-Mills for 4 point, this will be a tree-level Yang-Mills for 5 point, like that. So I hope the structure is clear where we are going. So, the thing is to understand what these vector fields are. So now I am going to explain to you what these vector fields. Everything, just our usual 5-point gluon amplitude for any helicity. For any helicity, yeah. And I am saying this right now for tree level, but the construction, hopefully I will try to argue that is their construction can extend to all loop of this Corolla. So I'll spend some time introducing their object, because I feel it's underappreciated and maybe it has many more potential uses that we have not found so far. So
you said it's 2D space.
Yeah.
And this
Is also in a 2D space. It's a vector field in 2D space, yeah. So this V2 is a vector field it's an antisymmetric tensor of rank 2 in a 5-dimensional space.
So it's not like a dual that 2D space.
No. These are exactly, yeah. No, it's not. I mean, here I'm phrasing it like this to just say that, if someone didn't give you anything else except omega and ask you like I want to write scalars, then the first attempt you would make is to find dual in that sense. If you have an n form, you'll find an n multi-vector field because they can be contracted without any metric, right? So like dumbest thing we'll try to do is to search some vector field like this, and you need some ingenious people like Cramer to tell you what these vector fields are. So Cramer didn't do it all like this. I'm paraphrasing what he has done because he didn't work with in Mandelstam space. He worked in the Schwinger space, etc. But how we are using his results, there is not much originality in what we have done. I mean, really, everything is coming from this. This. Yeah. This is Cramer SARS. I mean, I really feel this work. It really needs to be known more. SARS and WAN Com 2012. And then so their paper is really about looking at a given. I will say a little bit more, but much more was developed about for this polynomial itself in a very nice paper by Cramer and Yates. It was in 2013, I think. So I will spend some time explaining what their result is.
Object was for something which does not require a metric, so there is another way of constructing the. I mean, it's like f wedge star f, so which will require a metric.
That would require some metric.
And that also has a.
Well, so so I am giving one example. The other example is you can use this to define. It's a one form. So I can use a one form to define a measure on one-dimensional space. Those measures gives me phi cube amplitude. But I cannot define measure on the 2D space from a one form. So there are many scalars one can construct. One is like a volume of this guy, like this guy, or one is but that gives us some amplitude. And now I'm saying, but other geometric objects are look at some dual objects and contract them. That is also a scalar. So there are many geometric scalars we can construct without additional data on the kinematic space. One class gives us phi cube, phi 4, these kind of amplitudes, and the other, this class is giving us Gish theory amplitudes. Yeah. So first I'm going to tell you what Cramer did, because I think that even if you don't worry about Associahedron, I feel that this work is absolutely remarkable. So let's just forget about all this associahedron for a minute, and let's just focus on what Cramer first said. Then we will connect it with the associahedron. So given any graph gamma, now we are in usual quantum field theory. So given a graph, Feynman graph gamma, and suppose I want to construct like a Feynman diagram contribution of phi cube theory, like we do in our usual QFT. So now I'm not looking at amplitude, I'm just looking at a given graph contribution in phi cube theory to the amplitude. Then we know that there is at any loop order. So okay, please ask if something is not clear. So like gamma could be this, this, of course, our usual tree level. Gamma could be any of them. The only common property is that all the vertices are 3-valent. Okay, so given any 3-valent vertex gamma, 3-valent graph gamma, there's a standard result in QFT that like a correction to propagator, no?
If we fuse the first, the free ends of the second graph.
Say that again.
Join
This one.
Second one.
This one. This one?
Yes.
Yeah. No, we will not consider, because we are interested in amplitudes, so we will always have some external legs. Right? So it's a good point. I think that in principle you can, but we won't need them and we won't look at them. Thank you. Yeah, that's good. Some examples of trivalent graph with external, as he said, external edges. Then we know that in standard quantum field theory we say that phi cube theory, so let me call it evaluation of this graph for phi cube theory, for example. Just the evaluation is, you integrate over all the internal edges. So this is a usual way to write Schwinger. So please bear, if something is not clear, please ask me. So if number of internal edges, we call it E int. Then for each internal edge we put some Schwinger parameter, and then there is this. I will explain in a minute. I think that there are these functions. D is the dimension of space-time, and then we have this. There are what are called two graph polynomials. One I'm indicating by U, another by F, and F is actually a function of all the t's as well as the external momenta. So it's not very much important for us because to know what these are. Just want to say that there are these objects that you can completely create out of these graphs. So if you give me any trivalent graphs, I can write down what f and u are, and then I can evaluate this quantity, and then that gives me if they are trivalent graphs with say 2 cycles like this or 2 loops, it will give me contribution, Feynman graph contribution to this phi cube contribution of this graph. Is that point clear? So this is the standard thing. I'm not saying anything new, but you may not have seen this form of Schwinger, which may be not that much known. If yeah. So, but it's really not some novel thing. And now the point is what Cramer said is the following: that he is going to give us an operator based on this graph gamma, which is a differential operator in the momentum space, which I will spend some time explaining, such that this object gave us the gamma contribution to gluon amplitude. To any, so the graph can have any loops. That's why I draw these different loops. And so that means that this d gamma should be very, it should generate gauge invariant contribution, right? Which means it should have a ghost gluon contribution also. Everything should be there, not just gluon vertex contribution. So it is remarkable that from this Corolla polynomial that I will explain, he could give a differential operator which kind of take this guy which is generating phi cube contribution for a given graph, and this will create this operator. When it acts on it, it gives us the Young-Mills contribution, right? So that was Cramer's objective, and I will explain.
So somebody projects out the process.
Yeah. It comes out naturally from the Corolla polynomial. He doesn't have to do anything. So Corolla polynomial is some polynomial which was it has some other math connections, but you take that abstract, I will explain, abstract polynomial, and for variables of the polynomial you give some differentials. So it's like you represent a polynomial as an operator here, and it just creates for you Yang-Mills thing, including, it's a BRST invariant contribution from the graph gamma. No. Yeah. No, not for yes.
Didn't they show that
Yes.
sum of graphs also?
Yes. So that
Then can you
yes, you can. We have done.
back on the sum of forms?
Yeah. It's more subtle, but as we show in our paper, you can do that. So you can glue this together and also do that. But I won't discuss that. You are right. But let me now explain what this D is, because that's the main. Yeah. So that foregloon is because it's fixed by gauge invariance. It better come out of this action. It also produces quartic vertices which are mandated by gauge invariance. So the whole point is that D should be some operator which gives you BRST invariant Schwinger integrand for Yang-Mills. And it just pops out. I mean, you will see how. So I have to first now tell you. So the logic of Cramer was the following: given any trivalent graph gamma, there is some abstract polynomial which is called Corolla polynomial. Yeah. No, at this point you are in any. You can be in any D because this C comes with Lorentz indices which I have not contracted, and so that means that polarization I have not fixed. So you will see that the rules we give, they have the space for arbitrary D. So there is a Corolla polynomial, and this polynomial it's like a counting polynomial, which unfortunately I won't have time to go into depth of why it's interesting object in its own right. But given this abstract polynomial in terms of some abstract variables, you write it as you make from it some differential operator in terms of you replace, roughly speaking, as we will see, these variables by some differentials. And that is the one, that object we are after. So first I have to tell you what this guy is, and then what is the representation of this abstract polynomial for physics, for a given graph. That won't entirely solve our problem because we have to glue it in the case of Associahedron, but it's basically, gluing is really, it's not a big deal. So that the main thing is here. So let me tell you what C gamma is. So just only assumption is right now that it's a 3-valent graph. So I'll give you the most general definition, because just to show the power of this, so that you are convinced that it can be done for any loop. And so some nomenclature let me introduce C gamma. One is that given any graph like this, with every vertex there are incident edges. So with this vertex it is this one. So this is some nomenclature, okay, please bear with me. This one, and this one. So these three things are called half edges associated to this vertex. So you call this V1 and call this V2. So let's call this edge E1, let's call this edge E2. And so this one is let's call this edge E3. I'm going to call this edge H3, H4, H5 and H6. So H4, H3 are half edges, because they are incident on V1. H5, H6 are half edges which are incident on E2. Of course, H4, H5 are part of a single same edge. Okay, so but because E1 is an external edge, it's itself an half edge. So any external edge is a half edge, but trivially, because it's incident only on one vertex. Okay, so one nomenclature about half edge. I hope it's clear that there are 6 half edges in this for this graph. And then the point is that we define something called cycles, which is basically, if I give you a graph like this, and it's not a circuit, it's a cycle. What I mean is that this has 3 cycles. So this is one cycle, this is second cycle, and this is the third cycle. Okay, so these are 2 notations we need to define Corolla polynomial. Okay, half edge and cycle. And now I'm going to first introduce the Corolla polynomial for tree level graph and then say how to do it for, so any graph which has a loop will have at least one cycle. It's a kind of a trivial statement. So tree level graph will have no cycles, of course, 0 cycles. And now you just do the following thing. You associate to E1 every half edge, every vertex, associate a linear following. So for example, let me call it dV1, which is AE1 plus AH4 plus AH3. So A's are some random abstract variables, just variables, right? X, Y, Z. So with every half edge you associate a variable, and with every vertex you look at the sum of the 3 half edge variables, the 3 edges which are incident on it. Okay, so is that clear what we have done? And similarly dV2 is AE2 plus AH5 plus AH6. Okay, very silly thing to do like that. So if in that sense, if we are given this graph with E1, E2, H1, H2, E3, E4, then just I hope you see, right, what the Corolla polynomial for this guy is. AE1 plus AE2 plus AH1 dot AE3 plus AE4 plus AH2. Okay, that's the Corolla polynomial, and we can generalize to any tree level graphs, I hope, just by product at each. So these are called corollas. So this object is called a corolla, which is flower at each vertex at some sense. Okay, and now if you have loops, then it becomes more interesting. So if you, for example, have this loop, so I'll first give an example because then it will be clear what we are saying. So take this example. Okay, so it has one cycle. And you see that because it is a trivalent graph, at every vertex there is a unique edge which is not part of the cycle. So at this edge, at this vertex, there is only one edge which is E1, which is not part of this cycle, and at V2 there is an edge which we called A2, which is not part of the cycle. So now we define a corolla for this graph, C gamma, which is the corolla that we obtained from D, minus you take the sum, so minus so I will write then explain. AE1 dot AE2. So you take AE1 is the unique half variable associated to the half edge which is not inside the cycle. So you take product over both the vertices and multiply over the variables which were not part of the cycle. Okay, so now if you expand this, you see that there was one term here, AE1, AE2, that drop out, and then everything else remain. So now we can actually generalize it, and so basically the point is that we can write for any graph. So let me just, because of lack of time, let's focus on graphs which have only at most one cycle. But if you look at Cramer's paper, you can see that you can generalize this to any number of cycles. So let's just focus on one cycle. So any graph with one cycle, it is same as product over all vertices dV minus, if you have only one cycle, then it is product over the two edges, because there's only one cycle, right? So product over all the edges, I will write it scheme like this, which are not in the cycle. AH. Is this clear what we have done here? So if you have a wheel graph like this, then the subtraction term is AE1, AE2, AE3, AE4. Okay, that's the point. And the minus sign is what will cause ghost contributions to come. So that's why the minus comes. Okay, so this is a abstract Corolla polynomial for any graph with three valent vertices only and one cycle. But you can generalize this if you see Cramer's paper to arbitrary number of cycles. So if you have 2 cycles, then the contribution of 2 cycle will be with a plus sign, so it's an alternating sign. Yeah, yeah. Yeah. So this is coming from this is always going to come with a plus sign, because it's just to take every vertex and just look at a Corolla sum of the 3 variables and product. So that's what this is. Now the contribution which takes into account just 1 cycle at a time, that comes with a minus sign. If you have 2 cycles that I have not written, 1 at a time, it will come with a plus sign. 3 cycles, minus sign. So that's the rule to write this. Is that the question? Maybe I didn't. Yeah. Yeah. So these are all plus. These are all plus. These are all plus, right? No. So here they have a definition that if you have any vertex where you have 3 edges and every half edge has 1 variable, you add them. It's some abstract polynomial we are constructing right now, right? So it is your point is excellent, but you will see where your point becomes relevant. But it's not at this stage. These are definition of some abstract polynomial that we are writing, where there is no alternate sign or anything between these things. So interesting thing is that this object is all the, if you just expand this out and write, every term is positive. Why? Because you see that this subtraction, like look at this one. So AE1, AE2 is with a minus, but this has a AE1, AE2. Right? So it got cancelled. So what remained are all the terms which have only plus sign. And you can show this, that when you actually, for any graph with any number of cycle, if you actually write it down and expand it completely, every terms come with a plus sign. And this coefficients of every term is counting something, but that's a different statement. It's like some counting polynomial. Yes, yeah. Yeah, they have not in this form. They had an existence in the math literature in the sense Cramer was inspired by an object called graph homology, which was created by Kontsevich for a different purpose. So that was the underlying that structure was the underlying motivation for him to write this. And then there was a math connection prior and afterwards to these things. So now people have shown that these Corolla polynomials actually generate what is called graph homology. But that direct connection came after Cramer's paper, but the inspiration of this really came from earlier work of Kontsevich. Precisely the same, because it's homology. So I think that's where the it comes. Yes, exactly. Yes, exactly. So the signs, exactly. No. So the point is that it would. I mean, he saw that because that. Okay, this has a little bit of a long history. So people, his collaborator, this person, in 2009 he realized that if you take what we call BRST cohomology in QFT, then that has some abstract relationship with these graph homologies. So that already made an underlying connection that somehow to construct BRST invariant functions, we should work with graph homologies. And that was almost 3 years before this paper, but that was heavily used by Cramer as an inspiration, that and Kontsevich to come up with this definition of.
Just to see where this is going.
Yeah.
This was a graph in scale of IQ.
Exactly.
Then you acted on some operators.
So not yet. Right now we are just at this stage. I have given you some abstract polynomial. Now I will turn this polynomial into I will write it as an operator. I will represent this operator. Now that operator, we will see how that generates Yang-Mills amplitude for us.
That is going to generate just replacing those lines by wiggly lines, or is it going to generate a bunch of diagrams?
Bunch of diagrams where wiggly lines, quartic vertices, ghost and gluon vertices, everything together.
And that will be all the set of diagrams at a particular order in the
Yes, all the set of diagrams.
So the moral is that there is one operator which acts on a 5-cube diagram and generates
all of them.
All the diagrams, the Yang-Mills theory, and
Yes.
that particular derivative.
Exactly. So Cramer would give us contribution of a particular. So take the bare trivalent graph out of which all gluon graphs are constructed. This will give us all that contribution. Of course, we want to glue all of it, that we will do now. But this is what he showed. So his work is remarkable because he shows how in precise form this gives you BRST invariance and everything. So it's like very careful way. I mean, all the symmetry factors have to match, so it's a very exactly. I mean, the fact that this is one, this is one here, that is like that if you change this, you won't get the right symmetry factor. So he puts quite a lot of effort in showing that nothing is amiss in this way of. It's like something you of course know very well. This spinning up of Witten diagrams in ADS, except that the advantage here is that the contact terms come directly. You don't have to the split represent. I mean, everything comes from this operator, spinning operator. So let me now give a representation. Now I'm not going to give his representation which is in Schwinger space, but I'm going to give you something else which will help us glue in the Associahedron case. I'm kind of bypassing between his representation and what what we did a slight generalization with Amit for our purpose. But I hope this definition is clear. Yeah.
So maybe, for example,
Yes.
So you can have multiple
Yes.
So the result upon operating with this function operator on any of these two curves, diagonal curves, would result in the exact same set of.
No, it doesn't. It doesn't. Exactly.
What is the relation?
Yeah, the relation is that it's going to generate for a given graph only its gauge invariant cousins. So it's not simply that graphs here you are generating, even the labels of the graphs depend on what graph you started with. So there will be no, of course topologically it is true that you could get same graph, but then it would have not the same labeling. So yeah, all this he take great care in proving. No, contribution to Young means there will be no overcounting. There is no overcounting. In that sense, completely disjoint. Exactly. So I am now going to give so what I am going to now show is that slightly bypassing Cramer, how we can use this to construct vector fields in our kinematic space, and that basically is the maybe we can stop there if people are very tired also. So yeah.
Just pure two. You will get results in pure two.
So that's okay. So I was about to come to that. So what we are doing is of course generating only pure gluon theory, but after Cramer's work, we are generating full amplitudes, but for each graph after Cramer's work there were two works. One is by they are his I think students. One is David Pins, who showed how Feynman rules for spontaneous broken gauge theory can be constructed by looking at again spinning up phi cube from Corolla graph by graph. Another is this guy called Marcel Gauls, who he's trying to develop an efficient algorithm for parametric QED representation using this Corolla. So Corolla is general, and as long as you have gauge invariance where you only generate from a cubic finite number of vertices, they can all be written in terms of Corolla. It's where gravity, where this thing we don't know, because you need there's no end, right? How many you need for n particle you need n contact. So gravity is open, but for this it's very general for for example QCD, with matter, etc. Even I think David Pins has generalized it further. So you see the construction is such that it's about finding this is universal, and then you find some representation based on your matter content basically.
And the gauge group, where does that come?
No, because this is going to give us color ordered amplitude in Young mills. So gauge group is always a strip of. Yeah. Okay. So let me just tell you for tree level how this thing go. So I'm just going to give you the representation. So let's start with the simplest case. So they take this one for tree level first. So as we saw that the abstract Corolla. Let me write down. Was so let's call this H. And call this H prime. Okay, now let's look at this vertex first. I'm now going to give you representation of this in terms of differential operators. So let's focus on this vertex first. And let's say that just to begin with, let's say that the edges are all outgoing. Now one thing we need to do, because they're all planar graphs, of course they are sitting in a plane. So in the plane you choose one orientation, once and for all. But doesn't matter, you choose whichever one you want. So let's say we choose clockwise orientation at every vertex. Okay, so that means that once you have a clockwise orientation, you see that there is a natural cyclic ordering between these edges. So what I mean by that is that E1 is less than E2 less than H, but H less than, of course, E1 less than E2 and E2 less than H less than E1. Okay, I'm writing something dumb, right? Because it's cyclic. We have 3 ordering. So now now I'm going to write down what these terms are. So AE2. So because I'm looking at, it's AE1 plus AE2 plus AH. So I'm going to now give a representation of these variables in terms of differential operators. So AE2 is I will explain what the sign, where the signs are coming from. Sorry. Now these are our usual Lorentz indices, which will get contracted with polarization. So where is the sign coming? Because E1 is less than E2, so I have a minus sign here, because both of the edges are outgoing anyway. So everything is outgoing. So minus sign because E1 is less than E2, H is greater than, oh, I should put H here. Sorry, what did I write? And because H is greater than E2, there's a plus sign here. Now you can follow this logic, right? Just to give one more example, let me write AE1. And E1 is, H is less than E1, so okay. Now let me, just for completion, let me write AH, because that is important, because H is actually the only edge which is not external. So these two are similar, but I should have written AH as an example also. So this is, sorry, mu H, sorry, mu H, 1/2, because mu 3 is like, there's a 3 anyway for the external. So now I'm writing AH, and H, E2 is less. Okay, so these 3 are the 3 variables. Representation of the Corolla, the variables for trivalent vertex. Is the rule clear, like what we write? Now okay, we do the same for AV2. Now we multiply, so we get a differential operator. Every term is a quadratic differential operator, right? Because for this particular graph. And so now what we get is the following. Say that again. Yeah. That's an excellent. So we will come to that. So right now these are just operators. So this has nothing more than that. But we will see what they act. They act on the phi cube graph, which is a propagator. So of course it will act on the. So now you take this. So this is D. Let's call this is some. For this graph, it is D hat V1, which we have written down. It's this plus this times D hat V2. And now what you do is you act it on product of all the propagators. So you act it on 1 over product over I P I square, I equal to 1 to 4, and 1 over P. Now notice that PH and PH prime are same, because the same momentum flows through this half edge, right? So that, let's call that thing P12 square. So you take these guys where pH is P12, you just apply this, and you say that this one, so whatever you find, like this is like LSZ. You do this, and then you multiply it with the product of inverse propagators to just take out the external leg residue, and this precisely gives you two terms. One where you have the fusing of two gluon vertices. I will write explicitly. It's a direct computation plus the four gluon vertex. So now let me explain to you where the four gluon vertex come from intuitively. So you notice that there will be a term where pH mu2 acts on pH square. So right, I mean so we have AE1 plus AE2 plus AH acting with AH prime plus AE3 plus AE4 acting on this everything, right? All the product of all the propagators. Now you see that if you look at this term, which is this one, AE2. For example, when AE2 acts on AE3, AE3 has a term which is pH square dou by dou pH. So when this dou by dou pH acts on pH square, it generates pH square in the numerator, and that kills the propagator. So that generates the contact. Okay, so that's the logic. I mean, you can check by direct computation, and it's absolutely remarkable that the tensor structure is such that it will create for you this exactly the vertex contribution for a given graph like this. Okay, so I hope that at least the structure is clear, right? You can go and actually, so we have computed this in our paper, and check that that it works out nicely. So what we did was very silly, because let me just tell you the difference from Cramer, because Cramer writes all these operators in terms of Schwinger. So wherever you have this p square, he had 1 by corresponding Schwinger. Like, for each edge there is a Schwinger, so he had like 1 by T2, like that. And then we were for a while puzzled, okay, though it's not useful for Associahedron because it's acting on Schwinger, but T is kind of conjugate to p square, so we just thought, okay, let's just put p square and see, and then it just works out exactly as he said. So it was, so this is an example where, so now what is our vector field? Our vector field is V13. So now I'm giving you a vector field for 4-point case, which is V. Okay, now this minus sign comes from the Associahedron mutation. So every time you do one flip, exactly in a form, you put a minus sign. This is the operator we have written down, this operator. This one. But if you mutate, then you will write a similar operator where your graph was 1, 2, 3, 1, 4, right? And that will give you this operator. So you take this and you just contract it with dx13 by x13 minus dx14 by x14. And that gives you the tree level Yang-Mills 4-point gluon amplitude. Okay, so 4-point, now you can show, we show that it generalizes to n point for tree level. And maybe before going to one loop, let me see if this is okay so far.
Here, there doesn't be any difference, but there will be I epsilons that you need to put in.
Yeah.
Those will be automatically inherited from the scalar theory, or?
Directly from the scalar theory. Oh, yeah, exactly. I mean, one issue that, interesting issue is that if you had a phi cube met tadpole, then it's a bit worrying that why, because gluon tadpoles are like completely messy. So, what nicely happens is that, remember I didn't explain, but there's a corresponding polytope for one loop scalar integrand, where every tadpole is kind of doubled, like there are two copies of the tadpole, and this Corolla cancels the contribution. So somehow when you apply Corolla, in that sense, Corolla action on a polytope is better at one loop than for phi cube scalar, because scalar phi cube, this polytope, some of the vertices have tadpoles, but they are all in the, together they are in a kernel of Corolla. So when you apply Corolla, glue together, you don't get any tadpole contribution. So that's a nice advantage also. Okay, so I don't know if, yeah.
What would happen if you did this with just the contact diagram?
Say it again.
If you do the contact diagram, scalar theory.
No, so that's a very good point. So this Corolla constructed from trivalent graphs. So this you cannot apply, but you can ask if I have, is there a Corolla corresponding to quartic graph? And there is a Corolla corresponding to quartic graph. So we don't have a one loop answer or a polytope answer, but for a given graph we saw that you can use it to construct f cube. The higher derivative corrections in the gluon case also. So there is a Corolla, different Corolla, which will go from cubic to 6 point, for example, by contact. Right? You cannot, where every vertex is 4-valent. This you cannot apply, but there is a generalization that Yates and Cramer have provided in their paper. So I think I cannot say with definitiveness, but I think this procedure can be used to obtain EFTs of gluons also with higher derivative terms. But I don't have a proper analysis, just some examples.
And the more general thing is that now if you go to loops and you do a one loop diagram, it will give you all one loop diagrams.
Yeah, all one loop. You fix the external legs and planarity, of course, or whatever your order of planarity is, and then you generate all the diagrams for that with the gluon, including the ghost contributions. So ghost gluon vertices and contact, everything.
Right, and if there are two relative diagrams at the 5 cube level, and then you apply the same operator to generate all the...
Same operator means the operator representation depends on the label of the diagram, of course. So, right, here it's P, right, it's P1, P2, P12 is some label, right? So if you have P2, P3, P23, then it's a different label. So that as a function of momenta, it will be a different function. I don't know, is that the question you asked, or?
I guess at two loop level there will be a bunch of diagrams at 5 cube.
Certainly, yes.
Then those will have some relative factor. And
Yes.
then you will have different operators that are acting on each of these diagrams.
Yes, exactly. Yes.
And there is no such thing as a relative weight between the different operators.
Yeah.
Because the relative
Whatever symmetry factors are there, it's taken care of by symmetry factors, right? Yeah. So this for each graph, this is where Cramer's paper is very long. He took actually great care showing. In fact, he gives 2 loop examples that the relative weights, everything will work out fine. Every graph in 5 cube will give you a contribution with overall +1 if you want weight, with no discrepancy. And as he asked, there will be no. It's not like you will get like 2 evaluations, two graphs with same labeling from 2 different Corolla operators. Okay, I will just end soon. So right now, of course, tree level it doesn't matter. If you go to so where it matters where traces of eta come. So there you put D, and right now it's at for any D dimensions. Because we have not done the integration yet at the loop level, right? So the subtleties will come there.
Second is that you said Young will speaks F square, right?
Exactly.
Yeah.
Exactly.
What transcendence?
Yeah, that's a good point. Even just Chern-Simons perturbation theory, is it, or just Chern-Simons perturbation?
F square, Young is F square, and then you said 5-4 will give me
Higher order term. Yes. Yes.
Now I go the other way around. How will it be Chern-Simons?
Yes, it's a very good question. I think it should be possible because the underlying object is that you have Feynman diagrams dictated by cubic and gauge invariance gives you higher order. I think Corolla generates for you in principle that Feynman diagram, but for exactly what Chern-Simons I haven't. I don't think anyone has looked at it. It's a very, very good question. Yeah, I think it should be possible. Yeah. Okay, I just end now in 2 minutes. Like I just want to say about Associahedron what we do. So let me just give you one final interesting punchline about what is happening to the Associahedron when we do all these procedures of this contraction with vector field. And that's actually remarkable, I think, in itself, which we haven't completely been able to explore also. So here is what is happening. So at the level of triangulation, this is what Corolla is doing for you, purely at the level of triangulation. Because remember, every triangulation is dual to some graph. And what is Corolla doing to a graph? So let me now explain. I give for 4 point, but let me explain for 5 point. So you have CV1, CV2, CV3, like 3 operators. So it's a cubic differential operator. You apply, you can explicitly check. What it does graph theoretically is the following. It can either label every vertex with a gluon vertex factor, 3 vertex factor. So this is one. At the graph theoretic level, this will produce for you this thing, plus it could collapse this into a contact, and the other vertex will be gluon vertex, plus it will collapse this into a contact, and this vertex will be a gluon vertex. So I will label the, just for definitiveness, let me label the okay, and this is, of course, this is the, if you fix the ordering, then this sum is really the tree level gluon vertex. But notice each of this is dual to this triangulation. And so when Corolla acts combinatorially, what is it doing to a triangulation? It takes a triangulation and it maps it formally into sum of 3 triangulations in this case. So a triangulation where all the triangles are colored by these corollas, which corresponds to gluon vertices, or the so every vertex of associahedron gives you formally sum of 3 what we call marked triangulations, where either all the cells are marked, or if some cell is marked and an edge not adjacent to that cell is marked. And this picture of, so now our associahedron was something which was labeled by one triangulation. Now the effect of Corolla is that each vertex is labeled by this formal sum of these 3 triangulations, and this is precisely the model of this is an element of graph homology that Concept has constructed. So this combinatorial is a polytopy where each vertex is a homology of a triangulation somehow, and as we show in our paper, this is nicely related to gauge invariance of the theory. So nice combinatorial picture is emerging in the sense why associahedron didn't give us Yang-Mills, because each vertex was too coarse to understand the issue of gauge invariance. Right, sir?
What do you think? How is it related to
Because of the fact that
these are gauge images?
no, this one in this way, that the full, so this is the gluon vertex, but we know that from gauge invariance, once we have these, we must have a contact plus another one and this one. So combinatorially the picture of this, because this vertex is dual to a triangle, so either a triangle is colored or a triangle is colored and a remote edge is colored. So combinatorially, this is the model that is forced on us by gauge invariance of gluon amplitudes, and that is why associahedron itself was never enough to give us Yang-Mills amplitude, because you don't have this information. So this is some object that we are trying to understand, because in math this combination of this, I don't know why, but they have studied recently. If you label each vertex of associahedron with this homology, like what is the object? So people are actually studying it for some reason from 2019. So I think there is an object, what is called operad or something, which I'm trying to understand. So it's but I think there is some structure here that one needs to investigate further. Sorry, I didn't have time for one loop, but if you look at our paper, we show how the one loop integrand of Yang-Mills also comes from Corolla, the same way.
And say something about matter again.
Yeah. So the matter, the way it comes, I mean, I haven't done it, but at least in this, for example, Pins looks at let's say Goals looks at QED. So the idea is that this representation I put is this one, right? Like P square dou by dou P. So this you just have to make sure that at each vertex your A variables like A, B, C are such that when they act as differential on a scalar vertex, it generates the 3-point vertex of whatever theory you want, like QED for example. Then Corolla basically ensures that you will get QED amplitude. I don't know if that's what you are asking. So here, yeah.
Now can I see some structure as graph theory which is supersymmetric?
I mean, there's BRST.
Yeah, I know now how to couple matter. I know how to do a gauge theory. Now there should be some relationship.
Yeah, of course. Yeah. I mean, the point is that this has only handful of papers, and the problem is that these people are so much against supersymmetry that they wouldn't look at this. So I think someone has to just explore it. Yeah, but no one has looked at. I mean, it should be done. I agree completely. Because it's not found in nature. So he's yeah. I mean, he said in a talk that yeah. Yeah, there is some work actually. This is a work by, there is. There is a work by, but it will not be in the language of BRST, Cramer and Berghoff. They call it these homology operators, but it's the same. I mean, it's just a transcription of BRST to some graph theoretic language. So Cramer has said in this paper that he's going to write a detailed analysis of BRST from Corolla, like in physicist language, but that somehow never came. That paper didn't come. Okay, sorry, I just end. Sorry for going super over time. Well, yesterday and
Okay, thank you.
thank you.